pKa2 is 9.744. If you just spend a second, you can kind of look at all the different amino acids out there, and you'll notice that the pKa's of the species that are representative of the amino acid, they don't really change that much in their pKa. The first one's always around 2.3, and the second one's always around 9.5. Now there's a little bit of variation, and that could be expected if you think about what the R group is. Maybe that's a really good electron donating or withdrawing group. That was really impressive. I actually remembered a little bit of organic chemistry. Phenylalanine, got this big phenyl group plus an ethyl group. I don't know if that pulls electron density away or adds it, I forget. And then you'll see in a couple of the scenarios here, looks like in proline, tyrosine, and lysine, there's actually an extra proton, or I guess not in proline, I was mistaken here, but it looks like in lysine and tyrosine, you actually have a third species that the R group actually has an ionizable proton as well. But usually those come off at the last stage. So it's really hard to get this last proton off the lysine, and then you're pulling it off the alcohol group around the tyrosine here. So now you're getting at 10.8 and 11.0. You've got to get really, really basic. You're almost into the strong base category before you can fully deprotonate some of these amino acids. I don't think your body comes close to doing that in most scenarios. All right, so let's think about leucine, and if you've had biochemistry, maybe you're having flashbacks to remembering all the substituents and why the names don't come. There's no sort of rhyme or reason to it. Like I guess the methionine is easy because there's always a sulfur in it, but some of these other ones you're like, I don't know. I mean, the tryptophan is what the stuff that makes you sleepy after you eat turkey or something, right? That's how I remember some of these ones. All right, so let's talk about I guess the question is, we started with the question, is calculate the pH and the composition of 3 different solutions. So you go to the stock room, and they have 3 bottles on the shelf. They have a protonated leucine with a counterion ion, maybe chloride or bromide or something innocuous. You can get the leucine by itself, the HL form, or you could get a bottle of potassium leucine or sodium leucine. I don't know what form is the most prevalent form. In fact, I think you usually only get it in leucine form because I think the other 2 are not quite as stable unless you're in a cold room or something like that. So let's start with the acidic form. H2L+. As I've mentioned before, it's usually you get the Ka values as pKa values, mostly because it takes up less real estate on a chart or table like this. But remember, you can easily convert those in and out to the direct Ka values by taking the anti-log of it. So 10 to the minus pKa1, and so Ka2 would be P10 to the minus pKa2. So that would be 10 to the minus 2.328, which is about 4.70 times 10 to the minus third. This would be 10 to the minus 9.744, or 1.80 times 10 to the minus 10. Sometimes when you see them in like their actual numeric values, it makes a little bit more sense about what's going to happen here. You say, okay, well, the first acid it's not a strong acid by any means, but it's not a particularly weak one. It's still 5 times 10 to the minus third. There will be a little bit of it that's dissociated. And then you look at the second reaction and you say, gosh, that one's really not going to go much at all. It's 1.8 times 10 to the 10th, so it's going to be a very much smaller reaction. That will help us here in a second. So we could say that H2L plus partially dissociates and HL, the species, the intermediate form, that form, it really barely dissociates. In fact, the first one is about 10 to the 7th times stronger than the second one. But remember, those two reactions are linked, right? So you have to make a little bit of HL from the first reaction before you can even go to the second reaction, because they're coupled, right? They're not kinetically coupled, but you know, you have to be able to make this form before you can make the second form. Now, the good news is that we can make an assumption, or a cheat, whatever you want to call it. You know, at the end of the semester, I'm going to have more assumptions than rules, and you're going to be like, why did we learn the rules when we have all these assumptions? The good news is that we can say that a solution of H2L plus behaves as a monoprotic acid. And you say, hey, that's good news. I just learned how to do that this last chapter. Or maybe I will before the next test. But long story short is that we've already did this. We did this last chapter. So you say, cool, let's do it. Now, can you always make the assumption here? And this, of course, like all assumptions, you kind of have to test it after the fact. You can't just do it. So let's treat it like a simple monoprotic system. So H2L plus goes to HL and H plus for, you know, the Ka1. That doesn't mean that the second reaction doesn't occur. It does. It has to. It's got a Ka value that we know, but it's going to be really small. So most of the pH is going to be representative from this first reaction. And the small amount of HL that's formed, there's not that much of it to begin with, and it really doesn't want to come into the last form either, because that's a 10 to the minus 10th reaction. So for all practical purposes, we can assume that this is really the only reaction that we have to worry about. And you say, great, well, we know how to do that. So we'd say that, you know, Ka1 equal HL H plus over the concentration of H2L plus, and again, that should be a little bit familiar that we spent the whole last chapter doing. We say that these two things are equal to each other, so that becomes X and X, and that the formal concentration is both the acid in its forms. Now, F here actually encompasses the form of leucine in the completely deprotonated form, but we're also going to assume that's going to be really low as well, which we'll test it at the end. But otherwise, it's exactly how we have done our problems before. We have a constant, we have a formal concentration. I think I told you what those were, and then we solve for X. So let's do that. X comes out to 1.32 times 10 to the minus second molar. Now, in this particular example on the board, we wouldn't be able to make the assumption that X was negligible relative to F, so we couldn't get around the quadratic, but on a test I will. I'll find a way, because I don't like quadratic. I just don't like it. But you can see that that's a little bit harder to do in this example here when I said F was 0.05, so, you know, 5 times 10 to the minus second molar, you know, 1.3 out of 5 is not negligible. That's what, 26%. So you can't say that it's all, it's, you know, that minus X is not worthy. So if you do that, and we said that X was equal to the products of this reaction, these would be equal to 1.32 times 10 to the minus second. And the amount that's still in the protonated form would be F minus X, so 0.05 minus 1.32 times 10 to the minus second equals 3.68 times 10 to the minus second molar. And then minus the log of that would give you a pH of about 1.88. And the reason why it is a fairly acidic solution is that, you know, that Ka value is kind of big. It's 4.7 times 10 to the minus third. So it's not a strong acid, but it's not super weak either. So what happens in this solution is that you have a little bit of HL. You still have a little bit of H2L plus, and you have a little bit of H plus. all at kind of millimolar, I guess this would be about 30 millimolar or 13 millimolar concentrations. But we have to figure out our assumption. Can we still say that this is just a monoprotic system? Well, we can do it. Let's calculate the amount of the completely deprotonated form. Most of the time you wouldn't care about this. You'd be like, well, I got the pH, let's move on to question 6, let's get this show on the road. But we want to make sure in this case of a polyprotic system, if this was a truly monoprotic system, we'd be done. But we need to figure out whether or not this is really true. So to find the concentration of L minus, we need to go to Ka2. So you remember the second reaction relates to the intermediate form turning into the completely deprotonated form. So that would be L minus times H plus over HL. So let's rearrange this to solve for the completely deprotonated form. So cross multiply Ka2 times HL over H plus. Simple algebraic rearrangements. And you say, oh boy, how are we going to do all this? Well, the good news is we already have all those numbers. We have all three of those numbers, actually. We have Ka2, I said that was 1.8 times 10 to the minus 10th. HL was 1.32 times 10 to the minus 2nd. And H plus is also 1.32 times 10 to the minus 2nd, which if you think about it, kind of makes sense because you are making both of when you're making both of these species, you're making both a reactant and a product. So you can see again why this reaction is not going to want to go that much. It's kind of like a buffer where you have both sides of it already. But anyway, you calculate this out and you find that the leucine concentration is equal to 1.8 times 10 to the minus 10th molar. And I guess I would agree, hopefully you would all agree with me, that that's pretty low relative to 10 to the minus 2nd. So, it is a nanomolar concentration of the completely deprotonated form. But relative to concentrations that are 10 to the minus 2nd, you're almost a billion times higher or a much less. So the leucine concentration is there. I mean, the completely deprotonated leucine, but I don't even know if we can measure it. You might be able to measure it, I don't know. I never try to measure amino acids, especially not at nanomolar concentrations. It's not really a great form. So, when can you make these assumptions? You're always asking yourself, when can I make these assumptions? This drives me crazy. When can you make the assumption? You can really only do it when Ka1 is pretty significantly bigger than Ka2. In the previous example, although I just erased it, one of them was 10 to the minus 3rd, the other one was 10 to the minus 10th. So there's 7 orders of magnitude between the two. Now, when you don't have a big difference between Ka1 and Ka2, you would have a little, a pretty significant amount of species that would undergo the second reaction. So like say pKa1 is 2.3, but pKa2 was 4.5, then you couldn't make this assumption anymore, and you would have to actually figure out how much of the final product was made and how much that would contribute to pH. And you can do it. It's just quite a bit more complicated. So of course, what am I going to do for a test? I'm going to give you the ones where you can make the assumptions, and you can treat this completely protonated form as a monoprotic acid. So we can treat a solution of a diprotic acid like a monoprotic acid. which really means we're only taking into account one equilibrium step. You say, great, I got that. We got that because we've already done that one. And again, it's not changing anything that we learned in chapter 9, the previous chapter where we did monoprotic systems. So we've got one out of the 3 done. We know the pH and we know the compositions, which means we know the molarities of all the different species of the forms. And you say, okay, let's go on to step 2. Well, I'm going to jump out of order for a second, and I don't normally do this because I'm pretty by the book, but let's go to the completely deprotonated form next. So let's go 1, 3, 2, or ACB if you like. This would drive one of my sons. He likes to have everything ordered out. It would drive him crazy, but he's not here, so we'll do it. I gotta check my wife like he's acting up at school. That's what I really want to hear. Not acting up. He's sassy or whatever he's doing. All right, so let's say we have a solution that only contains the completely deprotonated form. Let's, for our purposes, call this the basic form. Not basic in that it's nondescript, in that this is itself actually a weak base, because obviously you can't lose any more protons. So it's going to react with water. This again is KB1, like we showed on the last screen. That goes to HL and hydroxide. And then, of course, this species HL can go back to the H2L form through the KB2 process. You might have already noticed, and this will be a little bit more apparent here in a second, is that HL can go both directions, right? So you can lose a proton, or it can gain a proton, and that will come into play when we actually have a solution of it. That makes that one the slightly trickier one. And then so KB1 would equal KW over KA2. Remember how we said a few seconds ago that you have to make sure that you're relating the right species to themselves. So that was 1.0 over 10, 1.8 times 10 to the minus 10th. That comes out to 5.55 times 10 to the minus 5th. Plus KB2 will go KW over KA1. So 1 times 10 to the minus 14 over 4.7 times 10 to the minus 3rd equals 2.13 times 10 to the minus 12th. So now we've got the players in this new game. We have a solution. The formal concentration is 0.05 molar. It's the completely deprotonated form. How are we going to treat this solution? Well, the good news, again, just like in the previous example, is that the first reaction doesn't go that much. It does somewhat. And then the second reaction really doesn't go at all. In fact, it goes, again, pretty weakly. So the good news is that we will treat L minus like a monoprotic base, which again, we've already know how to do because you learned that last chapter, or you will. Yeah.
So that Ka1 and Ka2, is it
Yeah.
those values
Yeah.
that we calculated
Right,
earlier?
yeah, they're,
Okay.
because we're looking at the same pair, so we can use those, so it's a self-consistent.
Okay.
All right, so the good news is we can do it like we've shown, and you say, okay, well, I kind of remember that a little bit, or maybe I will remember it here. So what do we say, KB1 would equal HL and OH minus over L minus. We will say that this is 5.55 times 10 to the minus 5th equals x squared over f minus x. Well, actually, in this case, I think you could make the assumption that f is greater than x because 5.55 times 10 to the minus 5th is pretty low, but it really doesn't matter. In this case, you will find, maybe you should do it all the way out, but on a test you would not make it such that you wouldn't need to. long story short, if you do it, you get an X value of 1.64 times 10 to the minus third. So out of 0.05, it's only like 2%, 3% dissociated, so it's not that much. So the amount of HL would be 1.64 times 10 to the minus third. The amount of hydroxide is 1.64 times 10 to the minus third. So the amount of H plus, if you remember nothing else from this class, is how to relate OH minus and H plus by KW. So this would be 1.0 times 10 to the minus 14th over 1.64 times 10 to the minus third. 6.11 times 10 to the minus 12th. So a pH of 11.21. Now, of course, if you forget to do this step, you would end up with a pH that's more like, what, 3.5 or something like that, or 2.5, I don't know. And so they obviously can't be acidic if you have a basic form. But anyway, what else do we say? Oh, how much of the leucine is left? That would be F minus X, so 0.05 minus 1.64 times 10 to the minus third is 4.84 times 10 to the minus second. So not that much of it's been lost. And we didn't really form that much of the intermediate form. But again, let's test our math. Let's see if our assumption is correct. Can we treat it like a monoprotic system? How much H2L did we actually make? So let's look at Kb2, H2L plus times hydroxide over HL. And just like in the previous example, we are going to rearrange and solve for the one variable that we need. So Kb2 times HL over hydroxide. And what did I say these were? Kb2 is 2.13 times 10 to the minus 12th. HL would be 1.64 times 10 to the minus third, and that's also the hydroxide concentration. So the amount of completely protonated would be equal to 2.13 times 10 to the minus 12th molar. So again, both of those are, I think the assumption is good, in that we do have a little bit of completely protonated form, but it's picomolar. I guess I'm not usually doing a lot of picomolar solutions. I don't even know if we can measure that. I'm pretty much guessing we can't. So you say, cool, can they all be this easy? Can we just have 2 chapters on the same stuff? Because I'm okay with that. You know, can we just have a test on this stuff? Because basically asking the same question the same 2 different ways. And so if Kb1 is significantly bigger than Kb2, you can treat the basic form of a polyprotic acid or polyprotic base as a monoprotic species. Which is really what we're saying in both cases, is that you can just assume that the second reaction is not happening that much. And it doesn't, obviously, it's not producing that much product. So you say, okay, if the completely protonated form really acts as a monoprotic system and the completely deprotonated form acts like a monoprotic system, what is this middle friend going to look like? So HL, I mean, the first and the third ones are pretty straightforward because they already have They pretty much have the kind of logic that you would expect from a monoprotic system. But this middle one is the tricky one. This is really the part of this chapter that gets a little bit farther afield. And it's the one we always do last because it takes the most time. The intermediate form, HL. So think about HL for a second in terms of what this species really is. It can do two things. It's, to use a non-scientific word, it's kind of tricky in that it can be an acid or a base. It can gain a proton to become more protonated. It can lose a proton to become less protonated. You say, which way does it want to go? Well, the reason, it really doesn't want to go either direction, quite frankly. So let's look at the actual values that we look at. So HL, if let's say we want to lose the proton, that is representative of Ka2 now. And we said Ka2 previously was 1.8 times 10 to the minus 10th. So it doesn't really want to do that much. Maybe it wants to do the other way. Let's see. What if HL says, all right, well, I'm not going to lose a proton, I'll gain one proton. And reform the protonated form. That would be KB2. And that one was 2.13 times 10 to the minus 12th. So one reaction is 10 to the minus 10th, the other reaction is 10 to the minus 12th. Leucine's like, I can do both of these reactions, but I would really just rather Netflix and chill. You know, I would just rather do something else. My son has found this out. Just find all kinds of stuff on there. I haven't looked at my bandwidth bill yet. It's going to be crazy. But the intermediate form can be like, I could do these reactions, but I don't really want to do either one of them. This one's low, and this one's even worse. Now, representatively, this one is a little bit stronger than this one by about a factor of 100. So in this particular case, you're going to form a little bit more of L minus than H2L plus. You know, and this sometimes could be true. So, you know, K, if you want to consider that the Ka value that they're talking about versus the Kb value that we're talking about. So Kb is a little bit bigger than Kb, or Ka is a little bit bigger than Kb. So should be, in this case, slightly acidic. Both reactions are going to happen, but this one will happen 100 times more than this one. So you're going to be producing a little bit more H plus than OH minus, but not by a lot, and neither reaction is going to go that much anyway. So, you know, you might end up with a pH that's slightly acidic, but it's not going to be huge amounts because neither of these reactions really want to go. The problem is we can't treat HL as a monoprotic acid, which would be great if we could. We would love to be able to do that. Just say, yeah, that second reaction doesn't happen. It doesn't happen that much, but relative to this one, it's only 100-fold difference. So Ka is not that much bigger than Kb. It's only, you know, really it's only about 100-fold. So 10 to the minus 10th versus 10 to the 12th. So while though both reactions are really not happening that much, you can't neglect the second reaction. So we have to account for both reactions because the values are just too close. Now, if this one was 10 to the 5th and this was 10 to the minus 12th, then we could still treat it like a monoprotic system and then say, okay, well, the second reaction just doesn't happen that much. And
How big of a difference should there be?
that's a good question. A lot of people have wondered. It's a matter of some debate amongst analytical. I mean, this is really what analytical chemists will spend their time talking about. I tend to say if it's greater than 10 to the third, if it's like a 1,000-fold difference, is a pretty significant difference, especially if you think about all reactions that are in play. Something that's 1,000 times more than another one, I mean, you've got the Olympics where people are winning by a split second. You know, if you do 1,000 times one over the other, then I'd say that's a pretty significant difference. Now, for purposes of our stuff, I'll always make it really clear whether you can assume it or not, but that's a good question. I mean, this is only 100-fold difference, and I still say it's pretty significant.
That you can
You know,
choose those
1,000 or
because
more,
if they
I'd
are
say would
close or
probably
if
be
they're not.
significant.
You can't
All right,
change it. There's no
so
proof because the values are just
we may not get through the rest of this
Oh.
today because I was running out of energy, but we'll see as far as we can go. So let's look at the charge balance equation. So how do we solve this problem that has multiple equilibrium? You're like, oh boy, our old friend systematic equilibrium comes back yet again. You thought maybe you were gone with it, or maybe you thought we put it on the shelf for a while. But it is going to come back. So what are our positive species? We have protons, we have completely protonated leucine, and then our negative species are going to be hydroxide and leucine, completely deprotonated leucine. And you say, okay, I've got 4 players in there, but none of them are the species I actually started with. That's going to suck, because I was given the concentration of HL, but that's not even in my equation. I'm like, oh, okay, I guess I'll figure this out some way. Let's rearrange this a little bit. Let's put everything on the left-hand side. So H2L plus minus L minus plus H plus minus hydroxide equals
that's
0.
sleepy.
So we've just basically
Thank you so much.
rearranged the equation and put everything on the left-hand side.
Actually, not sleepy today.
And the next thing we're gonna do is kind of relate each of these concentrations back to the only variable that we know, which is the HL concentration. At this point, you couldn't solve the problem because we don't have enough ways, we don't have those values to even solve it. And in fact, it doesn't help us find this value because it's not even in the equation. Well, the good news is we have 2 other equations that we can play with. We have a Ka2 and we have a Kb2, which relate HL to these other forms. So let's work with those for a second. Let's look at, I'm going to erase this, although this is what we're trying to get to. I need the lower space. All right. So H2L plus goes to HL and H plus, this is Ka1. And it does relate H2L plus to HL, and that's what we're going to need for this piece of the puzzle. So Ka1 equals HL, H plus over H2L plus. And I'm going to rearrange this now and solve for the protonated form. So that will be HL over H plus over Ka1. Give you a second to see what we did there. We just started with the most protonated form, and we said, here's a relationship between HL and H2L plus. Now, we could have done this in the base form as well, but then we have something in hydroxides, and as I'll show you here in a minute, it's easier if we kind of keep it all consistent. But we know now we have a relationship between one of the units of our charge balance equation and an HL value, which we're given, and an H plus that we're trying to solve for. So what we're doing is we're kind of isolating variables, to use a math term. I like math, if you haven't figured that out. More math than anything else, really. All right, so we have H2L plus. We also need a relationship that uses the L minus. So if we now look for a relationship between HL and L minus. This is Ka2. So Ka2 equals L minus times H plus over HL. So L minus is Ka2 times HL over H plus. Again, we're just rearranging the equations that we have. Now, if I was a really good professor, I would, show you exactly, how many equations we have and how many unknowns we have and that we can solve it. I kind of gloss over those a little bit sometimes. I'm sorry about that. I assume if we're going to do the problem, that we can solve it. Otherwise, we're wasting 20 minutes. All right, so now we have a relationship between H2O and HL and a relationship between L minus and HL. So we have two pieces of the said puzzle. And the other thing that we know is that hydroxide is equal to Kw over H plus. So if we have three relationships that we can now plug back into the charge balance equation. So if you remember, I'm going to rewrite the charge balance equation again because I ran out of the room. We have H2L plus, we have L minus, we have H plus, and we have OH. So now we can do the grand, to use a non-scientific word, smushing of the equations, or intercalation if you want to be more fancy. So this term can go over here, our L minus can go over here, and our hydroxide can go over here. So lots of threads. But the common theme to all this is that we're isolating basically HL, which is what we've been given, and H plus, which is the other variable that we want to measure for. If we do that, we can write a new and improved charge balance equation that takes into account everything that we just did. But it looks like a big bunch of gobbledygook, again, to use a non-scientific word. So this would be H plus times HL over Ka1 minus Ka2 times HL over H plus hydronium concentration. That one didn't change. That's the only one that didn't change. Minus Kw over H plus equals 0. I think I did that right. So hopefully we moved everything to where it should be and made this charge balance equation into this new charge balance equation. Now, the good news is, as you can see, is that you have constants a lot of places. You have a constant and a constant and a constant. Those are good. And the only other variables that we have are HL and H plus. But unless you're like a math genius, and I'm not certainly a math genius, you're still saying to yourself, how am I going to solve this? This is going to still kind of suck. The first thing to do is we want to try to solve for H plus. So the first thing I want to do is get rid of these H pluses at the bottom. So I'm going to multiply both sides of the equation by H plus. That doesn't do anything to the 0 side, so that's good. The good news is that we'll get rid of all these things at the bottom, and that'll help us kind of clean up the equation here in a sec. So now the new equation, the new 2.0 equation, maybe it's 3.0 if you really want to be consistent. So if I multiply everything by H plus, we get rid of this term, we get rid of this term, and everything else gets scaled up by an h plus. So now this is h plus squared. This is also h plus squared. And what we're also going to do, this is certainly, I'm kind of showing you how the sausage is made, and then I'll show you the kind of the take-home equation, but I do like to show you at least how it's done, so it's not just magic. I'm like, yeah, here's an equation, you just use it forever, and I never know how it works. I hate that when people do that, actually. I want to know how it's done. I don't like magic tricks, because I want to see it. I want to be like, hey, can you explain how you made that disappear? Like, yeah, we don't tell people that. And I'm like, I kind of need to know something. That's a problem with mine. I really do. I need to know. It's just, I don't like the magic part of it. What kind of wires did you use? What did you use for that? So I'm going to take anything that has an h plus squared out. I'm going to kind of isolate those terms. So this one has an h2 plus. This one has an h2 plus, so this becomes, if we pull it out, so we have h2 plus squared, multiplied by HL over KA1 plus 1 minus KA2 times HL minus KW equals 0. And you're like, I'm just rearranging the deck chairs on the Titanic at this point, you know. We're just moving it all around, but believe me or not, it will hopefully make a little bit more sense here in a second. Next step is move everything from these two that are negative, we're going to move them to the right side of the equation. So charge balance is still being changed around.
Do we not have a plus h2 squared on that stuff?
Well, this becomes the 1 here. If you think about this multiplied by this is exactly that right there. So I just pulled that out of the equation and isolated this because it's common to both this term and this term. HL KA1 plus 1 equals KA2 HL plus KW. And what do I have to do next? Oh, okay. So we want to solve for H plus. So we will divide both sides by what's in parentheses. Gets better and better. We now have a relationship that has so many different things in it that I don't even know how it's all going to come together. At this point, I will sort of claim a little bit of a magic step in that I don't really want to go step by step how this turns into the next equation, but it's not magic. It does happen. You'll have to take my word for it, or if you don't, you can figure it out on your own time. This becomes KA1 times KA2 times HL plus KA1 times KW all over KA1 plus HL. It's kind of like the quadratic. I mean, you can do it if you have to. It might make you physically ill if you have to do it, but you can do it. And you can rearrange this to turn into this, and maybe if you're better at this kind of algebra than me, you're like, oh, of course, well, you multiply that by that, and then you make this turn around and blah, blah, blah. And if I was a better professor, I would do that for you. And so the last step, of course, is this is h plus squared, so we can just take the square root of that to solve for this equation, as shown, is the way to calculate the pH of a intermediate form of a diprotic acid. And if you want to, you can use that equation. But what will Dr. Stanley do at the next stage? Anyone guess? What will he do to save you from brain cells?
Not make us do that.
No. Nice try.
Simplify.
Simplify. We gotta simplify. If you run into a crunch and this is the only way you can solve the problem, then go nutty and do it, you know. But what, of course, we will do is start to make some assumptions. What can we assume first? Well, the first thing we can assume is that the amount of acid that we started with is really equal to the HL, because neither one of those equations, although I erased it a long time ago, are going to turn that much. So pretty much what we put into the solution of HL is going to equal HL, because one of them was 10 to the minus 10th and the other was 10 to the minus 12th. So, you know, both of those are not going that far. So let's rearrange it a little bit more. And the good news is that we can use the value that we were given, the formal concentration, in the problem now.